quite useful for me to gain the basic understanding about what's happening based on the topic. But again, the most difficult part I think is regarding the assignment because I never had the fundamental about this thing
Okay.
because during my degree time also I'm taking power system engineering, quite
Ah,
challenging.
okay.
So it's
Okay.
quite challenging at the first place. But
Okay.
somehow I managed to pick up few basic things about the topic. Somehow I think the most difficult is when I try to understand about the SDRAM itself.
The
So
SDRAM
that's
itself, lah. Okay, okay, okay. So the challenge is really understanding the SDRAM and sequential state machines. That's where you guys are stuck, lah. Okay, noted, noted. The reason I'm having this session is also because since there's only two of you taking these two courses, I want to tailor it a little bit more to your needs, lah. Because I understand that both of you probably may not have too much interest to go into IC design industry, but these kind of things are also okay. So what I'm sort of saying is just we have quite advanced in the semester already. So I want to actually like modify the content a little bit so that I don't overburden you and also so that you can do well, decently well in your final exams because I'm still in the process of setting the exam questions and all that. And I want you at the end of the day to take home something valuable from this course. You don't, because it doesn't make sense to just try to throw everything at you and then you don't learn or you just feel overwhelmed. It's more important to actually say, okay, maybe for with your time and all that, you can pick up to this much. So let's focus on you being able to understand that. So I think as a core, it'll be great for you if you can understand, learn once and for all how to do good state machine design. What are the principles for that? Then if you can understand what's this whole big idea about SDRAM, how are they organized and all that. So I've listed a bunch of modules here as you can see. Let me go back to share my screen. Okay, so you feel free to interrupt me at any point in our discussion lah, because this is actually meant to be two-way. I'm doing what I can, my best to actually just really tailor this to your needs lah. So let me first start by sharing a little bit what is the philosophy of this class, what I'm hoping you get to pick up. And then in that process, let's have a discussion about what really you think it's feasible for you and if of your interest to pick up. And then we'll try to trim some of the material that I have up here so that you will just be really good at the things that you can master lah. So the goal of digital systems design is it was supposed to train you to become a systems designer. That meaning that anybody can throw you any specification. They say, I want a digital circuit that can do this or that, right? And it's moving beyond your basic digital electronics. Basic digital electronics, I think it's more of like you're talking about single circuits lah. You got 4-5 inputs, maybe like 4-5 outputs. You can design a circuit lah. So DSD is meant to go beyond that, and it's meant to integrate not just the digital circuit part, but you have to learn how to deal with memory. Main memory lah. SRAM is one example. You have to learn how to deal with like interfaces, like how do you actually exchange data between digital blocks, and you have to actually solve a little bit of the interconnect. That is, how do you actually design connections between blocks, digital modules. Your lowest quality interconnect is actually your bus lah. So you probably might be familiar with the SCI bus or the I2C bus or the SCI bus. They are both serial buses where all the circuits are actually sharing the same wire, and then whoever speaks first, whoever drive the line, everybody else has to listen. But they are more advanced interconnects. For example, the crossbar interconnect, this is typically seen in routers. And then finally, you actually have point-to-point interconnects. And then you also have networks. Networks like your IP, your routing in internet, right? So those are also forms of interconnect. That is, how do you get data from one part of the one module to another module? So the philosophy is actually to cover all of this lah. And the reason I chose memory, there are several reasons as the design example. So the philosophy is you are supposed to learn all this through hands-on experience actually designing a significant digital block lah. And in this case, it's actually the SDRAM circuitry lah. Right? Why memory? Because memory itself, actually, if you look at it, it's not just memory anymore. It's not just like your simple SRAM where you just put in a chip, you put in address, you get out data. Nowadays, memories are clocked, and there's a lot of parallelization and a lot of like scheduling and interconnect. So all the modern digital design techniques, you actually can apply them to memory. So if you study and learn how to design memories, you can also apply this to processor design. You can also apply this to video codec design. Like all these things can be applied. It's more like the motifs, teaching you the general techniques how to design all these. And then what I'm actually advocating is we have a bunch of open source tools. Of course, the commercial tools are going to be way more accurate and things like that, but the open source tools are pretty good nowadays already and allows you to do pretty complex design. And I've actually set up the Docker and the computing environment so that you can actually run this really easily on your laptop at home. It's not going to take that much time. I've already done the heavy work of actually putting together and making sure the installation works and all that. So the simplest way is for you to install Docker. Docker is a virtual machine management software. Then you install the container, which is basically an image of the entire file system that I've set up for you to run this. And then you can hit the ground running with your simulation and synthesis. But there's also another option for you, which is you just go online to EDA Playground. This one is even simpler. Everything is graphical user interface. You can just do your simulation there and all that. And simulation to figure out your, whether your design works or not. Okay, so there are two things it seems this morning that I will address in a little bit more detail. One, I like to go into deep detail on this idea of state machine design, sequential state machine design to really reinforce your concept. Second, we will talk about in quite some detail what is an SDRAM and how is it that different from an SRAM and why do we need to go into SDRAM. You can of course read much more on that. I've given you the resources like the Jacobs textbook and the Optimizing DRAM Timing 2015. You were supposed to actually read that, but I recognize that in practice, especially you guys are working, maybe you don't have that much time. So that's why I said, okay, let's sit together and see what exactly would you benefit from learning in this course, and then we try to trim the curriculum a little bit so that you can go home at the end of it, you feel like you've learned a few valuable things. It's at a master's level. You're satisfied, your grade is good, and things work out that way. Okay, so if you're both okay, let me just move on to a whiteboard now, and I'll start trying to see if we can go through the state machine fundamentals. Okay, let me see details. So I just beg your pardon, I'm still learning this Microsoft Teams thingy. So previously I was able to share a whiteboard, but I'm not sure why now I can't see the button. Okay, let's see. Let's try freehand. Okay. Okay. Meeting notes. Okay, it's not meeting notes. Okay, it's not notes. Okay, I'll do this in PowerPoint.
I think you need to find it in the apps.
The app section. So there's Teams. I'm going to Teams and there's a section where you can add apps. I tried adding. Oh, I see. Then you can add you can just click on it and then you can view it, right? Okay, I see. Great. MSC. I'm trying to add, but it's not allowing me to add. or maybe OneNote lah. That's what I hate about this online learning thing. Who's supposed to be there, and then when you want to use it, it's like oh, we're taking longer to load and things like that. And you're like, what is all this cloud stuff that promised you?
But are you using the app or the desktop?
I'm using a desktop actually, because usually the desktop has more features.
Yes, yeah.
Yeah, I'm actually on a desktop and on a pretty fast connection. I think I can still. Okay, so can you see the OneNote file? I put it in the MS Teams channel. Do you think you can see it? Maybe you go to the stream and you can check it out. Can you check and see? Give me some feedback whether you can see my little scribbles.
You know work yeah, Asia?
Hello, Daniel, Alvin, can you just check
Yep,
whether
yep.
you can see it? Huh? Okay, great.
No, we can't see it.
You can't
I
see
can't
it.
see it.
Okay, it's not going to be the MS Teams. This one. How do you get to MS Teams actually? Because I've added you to the MS Teams class. Can
Mhm.
do
Is
you
it in
have?
the?
It's in
Yeah.
the streams on the class.
Okay.
So there is the meeting, which is just like you click and then you just get into this meeting. But there is also supposed to be a MS Teams where I've added you as students in the class. So you're supposed to be able to see, like, maybe it's like a Facebook feed like that, right? So it's actually added on the feed, and there's a link MSc ASC ADSD sequential machine lah. That's the one that I need you to see if you can see that or not lah.
Okay,
So
give me a moment.
Okay, I will share my screen so that you can see what it looks like on my end. So on my end,
Didn't eat this biscuit. You want or not?
okay. Share.
You can see the whiteboard.
You can see the whiteboard. Okay, then I'll
Loading,
just
yeah.
I'll
It's
just
loading.
I'll just use the whiteboard lah. Yeah, fine. I won't use the version. Yeah. Okay, you can see the whiteboard, huh? Okay.
Yes.
Wonderful. Okay, great. Let's start.
Something went wrong.
Something went wrong now. Okay, let me know once you can see my first D flip-flop.
Okay.
Okay, do you see the D flip-flop?
Yes. Thank you.
Yes, okay, great. Then I can start. Okay. What is this this principle? Okay, let me just go ahead and mute you guys. Great. So you just have to unmute if you have a question. Okay, what is this principle of sequential state machines? So typically the way we start teaching in undergrad is we tell you there are something like called states, right? So we call this like, let's say state 0, and then you have something called state 1. Okay, they start with this state transition diagram and they tell you that, okay, you know, I'm actually moving from state 1 to state 0 and state 0 to state 1 and then state 1 to state 0. And sometimes they actually have some input value here that they say is this transition. So that's the level of the way the concept has been introduced. But I'd like to go into a little bit more depth to share with you like the philosophy of that. The reason we actually have state is because you know, when you have like a combinational logic, if you are going to be, so can you see my arrow? You can see my arrow moving, right? Just type yes or no lah, or you can just unmute and let me know. Do you see my arrow moving? If you don't see anything arrow moving, and if it's just a static drawing, just tell me it's a static drawing, because I don't know what you can see then, so that I can indicate. So what the arrow is actually supposed to be moving around the red line. Do you see it? Hello, hello, hello. Hello? Hello, guys?
You can see the red line.
But you don't see an arrow. Do you see an arrow here?
No.
No arrow. Okay,
No
great.
arrow.
Fine, fine. Then I have to actually use the red line to indicate. Okay, okay. Thank you, thank you. Okay, I'm going to use this multicolored. No, no, the red line will be better. Okay, right. So if you see like this NOT gate, this AND gate, you put some input here. It goes through some kind of propagation delay. There is a delay from the input, you putting the input to the value coming at the output here. This one I think you can understand because nothing happens instantaneously. Then you put some input here, you put the value at the output here. But the challenge becomes in digital circuit design, what happens if you actually want this output to help you make decision for the next computation? How do you capture this output here? How do you freeze it in time? So the way we do it is we actually break up, we actually put it through a flip-flop because the flip-flop actually acts like a memory because whatever you put in here after one clock cycle, it goes out. So the concept of a sequential state machine, okay, so now I'm drawing you the clock signal actually, okay. The concept of the sequential state machine is that is actually a kind of synchronization. Why do I say it's a synchronization? Because what you say the sequential state machine is at all the positive edge of the clock. Okay, that's when stuff happens. That's when the circuit is supposed to synchronize itself. So what when you design sequential state machines, what you're actually doing is you got a bunch of flip-flops. Okay, these square boxes are a bunch of flip-flops, and then you've got a bunch of like what we call a cloud of logic here, CL. But these are basically like your NOT gate, your AND gate. You know, it's computing something, okay, and the propagation delay, the time for you to actually compute through this cloud of logic, it will be slightly different for each input to each flip-flop, you see. It'll be slightly different, right? Because the type of logic operations that you will put in will be different, right? Some gates you will have inputs will be like AND gate, OR gate. Some gates you have like 5 AND gates. Some gates you have like 2 NOT gates and something like that. You know, so it's a bit different, right? So what the sequential state machine does is between one clock edge to another clock edge, that is the time at which the combinational logic from all the combinational logic that's supposed to feed the flip-flop, that's the time range it's given to actually compute the next value that you want it to remember. Okay, so that means that you have when we design the circuit, we actually have to design this combinational logic here, this combinational logic, and this combinational logic, and this combinational logic, so that it actually needs to compute. You put an input, the input will arrive at this clock edge. That input must lead to a new output before this second clock edge. Okay, so computations in a synchronous state machine is still done by the combinational logic, but the difference is that the combinational logic has to perform its computations within one clock cycle or less. All right, so that part is clear. So if you do it this way, at every clock cycle, the positive edge of the clock cycle, this value will be updated and remembered in the flip-flops. And it's kind of nice because once it's remembered in the flip-flops, you can bring it back here and put it into the combination logic as an input. So you can actually make computations based on past values. Why do I say past values? Is because the value of this blue part here, that is the output of the flip-flop, is the value computed by the circuit at this point, 1 clock cycle before. Okay, this blue value, okay, let me use a different color. Let me write this. Okay, I use blue and maybe yellow lah. Okay. So this blue value arrives at this point of the clock, whereas the yellow value was computed somewhere here lah. Okay, that part is clear. So you are now able to make decision, a new computation using the blue value, okay, during this clock cycle here. So the sequential state machine allows you to remember and to capture a value from a previous point in time so that you can actually make a computation based on it. You can make decision based on it. Okay, so this is something like, let's say you want to say something like, a simple example would be, let's say you want to know whether you receive two sequence value. You want to know whether you receive the sequence 1 and 0. Why? Because maybe 1 and 0 is the beginning of a text file or something like that. Okay. So you need to remember that you've received the logic 1 first, right? So if you received logic 0 previously, you need to remember that you didn't receive logic 1, right? So this is an example of why I need to remember past values to help me in my decision making. So a very extreme example would be, again, in your laptop computers, right? Let's say you want to start up your laptop computers are extremely complicated, right? You have to load the operating system. After the operating system is loaded, then you can start loading the programs, then you can start having the mouse. So the operations are actually a sequence of operation that depend on the previous one. Or example would be your for loop, right? You want to calculate I equals I plus 1. Right? So you have your initial value of I, then at the first loop, you need to remember what is the previous value, right? So of I, so that you can add 1 to it, right? So that's an example of the case of how I want to remember. I need to use values calculated at some point in the past, but I need to use it to calculate a new value. Okay, so now we have covered the concept of memory, that sequential state machine actually are a form of memory. They actually remember values computed in the past so that you can use them to to compute now. Now, what is the reason you need this memory element? Is because if you take the output here, so let me go and use yellow lah. If I take the yellow output here and I feed it back, I might have a problem. You know why? Because I actually have two paths to compute this. There's one path here and there's another path here. Okay, so this yellow value is actually going to go back here, or maybe I can draw another circle lah. Let's say I draw maybe an OR gate here. I have an input here, and this yellow value, let's say I want to bring it back into this computation here. I have a problem, right? Because in order to calculate this yellow value correctly, I need to evaluate this first path. I need to evaluate this second path. I need to evaluate this third path here. And because of the propagation delay, maybe this path will come first, and then you might give you an intermediate value that is different. That's not the final value. But you already feed that in here, and then you already kacau this part here, right? So this is what we call races. That if you just take this value here and feed it back, you may end up getting the wrong calculated yellow value here. So that's why we need a flip-flop, because not just to remember, but to decouple, so that this value, when it comes out here, it won't disrupt the calculation of the supposed desired value here. So this is the second reason why we are designing synchronous state machine. First, we need to apply and remember a value from the past. The second, in calculating and using that value from the past, you want to make sure it doesn't affect the computation of the yellow value. Okay, so you need to only apply it later. Okay, you have to control the sequencing in time. That's why it's called synchronous, because at the positive edge of the clock, this is when the updates happen, and this is when you start a new computation across all the combinational logic. Okay, now I'm going to now start talking about how this state transition diagram actually maps to this particular circuit here. Okay, you've probably recall in UTP we thought that each state is represented by a combination of flip-flop value lah. This is the state assignment problem lah. So you can think about the state as remembering something. In fact, the state is actually a memory of some value lah. Okay, so the value that was computed previously, okay, is stored here. That's a particular state. Okay, let's say 0, 1, 1. Okay, 0, 1, 1, we always think about it as a number, of 3. Okay, 3 is a state. Okay, but I hope you understand that what we're trying to remember is actually a unique combination of flip-flop values. Okay, that is a state. Okay, and it is up to us, the designer, to assign meaning to the state. So for example, the state can mean that I've received a logic 1. Or in the case of DRAM controller, the state can mean that I've received instruction 1. Or in the case of maybe a PC, the state could mean I've received the first of the 4 loop instructions, but in assembly. So assembly instructions actually can be thought of as a state. Each assembly instruction is actually one state because it leads to one unique combination at these outputs, and these unique combinations will specify some unique calculation here. Okay, so a state is basically a situation in time of that circuit, and the situation in time is basically the best way to think about it is just what is the circuit remembering at that point in time. Okay, at this point, is it clear what I'm explaining, or do you have some doubts that you want me to clarify before I move on? Can you turn off your microphone? Give me a bit of feedback.
So this is called the what the triggering of the signal is called a postage, right? Right.
Yes, the triggering of the signal is called a postage because the signal. So okay, let me refine that a little bit lah. So you are right that you're saying that the update of the flip-flop happened at the pos edge, the positive edge of the clock, but that does not mean the signals are changing at the positive edge. The signals in the combination logic, they are changing. They are changing all the time, and they will settle somewhere within this clock cycle, depending on the propagation delay and all this kind of stuff. Okay.
Okay.
We have not discussed what is this computation yet, but I just want you to have that concept that there's computation is done by combinational logic, and at some point at the pos edge of the clock, it is that final value is already settled for that particular clock period and is remembered by the flip-flops. That's the concept I need you to grasp at this moment.
Okay.
Okay, and then the next concept I need you to grasp is that if I look at the collection of values remembered by a group of flip-flops, that can represent some condition of my digital circuit. Do you think you can grasp that concept?
Meaning that the outputs of multiple flip-flops or D-latch, is it?
Yes, that's right. Okay, let me distinguish a D-latch and a deep flip-flop are similar, but they're not actually the same circuit. A D-latch, the value can change throughout the positive high, and the value doesn't change at the positive low. Okay, so a D-latch, the synchronization happens over a period of time. A flip-flop, the synchronization, the update happens only on the clock edge. So they are quite similar, but they're actually a bit different, right? And it's this idea of synchronizing. When does the synchronization happen? Synchronization means all the flip-flops in your circuit will remember the value at their input at that point in time. Which means at that point in time, when the edge comes, all the combinational circuit must have already generated their steady output, the yellow part here. Is that clear or not, Alvin?
Yep.
Okay, good. So now if you can accept that the flip-flops are actually remembering some values computed, and then there are a bunch of them, and all of them taken together, you know, they're the combination of 1 and 0s lah. Okay, and so if I actually have, let's say I actually have 4 bits, if I have 4 bits, okay, there are 16 possible combinations I can have lah. I can have 0, 0, 0, 0, Okay, I can have 0001, I can have 0010 and all that lah. So 4 bits allows me to have 16 different conditions because it's just the what values they hold lah. 2 bits allow me to have 4 different combinations. So if I look at the values remembered by the flip-flops, okay, and here I have 3 flip-flops. 3 flip-flops will give me 8 different combinations, right? 000, 001, 010, 011, 100, 101, 110, 111. Okay, 8 different combination allows me to represent 8 different situations. And this is the part where the designer is starting to give meaning to what your circuit is doing. So when we design sequential state machines, what we are saying is that in practice, we want our circuit to remember certain things, and we want our circuit to be represent that it's in a certain operating mode or certain operating condition. So how do we do that? We need to remember that we are in that situation. And the way we do that is we assign meaning to these combination of flip-flop outputs. So maybe 000 could be state 0. 001 could be state 1. Okay. Can I say 111 is state 0? Of course I can. Can I say 101 is state 0? Of course I can. It is up to me as a designer to assign the meaning of the flip-flop values to represent possible combinations. Okay, so what I'm trying to actually share with you is this deep concept, a very fundamental concept, that a combination of flip-flops can represent different conditions. If you need to represent 30 different conditions, you need 5 bits, because 5 bits can represent 32 different conditions. That means you need 5 flip-flops. If you need to represent 100 different conditions in your circuit, that is to remember 100 different conditions, you need 7 flip-flops, because 7 bits can represent 128. You cannot represent 100 different conditions with 6 bits, cannot, because 6 bits only give you 64 conditions, okay? So this whole idea of state machine is basically the idea that we are giving meaning to a particular condition, and we are saying that this condition is represented by this particular bit pattern in the flip-flops, okay? And the way you've thought about this is you've been taught to design a counter, but if you think about it, the condition I want to represent in the counter is actually the values from, let's say, 0 to 8 or 0 to 16, because I'm counting. So each count is actually a condition. And if I want to count up to the number 10, I need 10 numbers, okay? Right? But it's not just counting, right? So what you the students tend to associate is they tend to associate that, okay, these bit patterns from the flip-flop is a number, okay? Yeah, it's a number. It can be interpreted as a number, but you must understand that it can be interpreted beyond just being a number. But yes, it is a number, okay? So that part, do you understand? Do you get that? So this is the reason why, let's say I give a simple example. If I have an automated washing machine in my house, right? Your washing machine actually is a state machine. Why do I call it a state machine? Because it does certain operations in a sequence. Let's say you want to have a quick wash. A quick wash means first thing you have to fill in the water. After the water is full, you stop filling, then you start spinning, rinsing. That means you just move the motor back and forth, back and forth. After some time, like 5 minutes, you drain. Okay, after some time, the drain finish, you do a spin. So you see, you're moving the machine in a sequence of steps. And why it's called a state machine? Because I can represent the operation of a washing machine as a sequence of states. The first state is you fill up the water. The second state is you do the rinsing, the back and forth motion of the motor. The third state is you use drain. That means you empty the water. The fourth state is you do spin. That is you rotate the motor in one direction very quickly so that you can dry the water. Then you can repeat again, go back to the first state, which is you fill up water. And if you do a short wash, you only maybe do 1 round of that cycle. If you do a long wash, you can do 2 rounds or 3 rounds of that cycle. But if you represent that as a state machine, state 0 is filling the water. State 1 is doing the wash, or you can actually bring that up into 2 states, state 1 and state 2. State 1 is forward motion spinning. State 2 is reverse motion. State 3 can be the drain. State 4 can be the spin in one direction. Then you can actually go back to state 1. And how would I represent this? I can represent that state actually as outputs of my digital flip-flop. Okay, so I already had 4 states, 5 states already. State 1, state 2, state 3. It's 4 states. 4 states. How many states? 5 states. State 1, state 2, state 3, state 4, state 5. 5 states for the washing machine. So I need a total of 3 flip-flops to represent that, where I can assign state 1, the filling water is 0, 0, 0. State 2, the forward rinse is 0, 0, 1. State 3, the backward rinse is 0, 1, 1. State 5, the drain is 1, 1, 1. State 6, the emptying the water is 1, 1, 0. I could do this kind of mapping. Okay, so now if you understand that I actually, in most digital circuits, is actually implementing a sequence of operation, and that sequence of operation can be represented by a combination of bits of the flip-flop, then the process of designing the digital circuit becomes easy, because then I just need to decide if I'm at state 0, 0, 0, that is rinsing the water, when do I switch it to rinse? Okay, I switch it to rinse after the water level is full. So in order to change the states here, because I need to change from filling up the water, which is 0, 0, 0, to actually rinsing, to rotating, I need to change the representation from 0, 0, 0 to 0, 0, 1. Okay, because if you change the state this way, there will be a circuit that will look at, okay, if it's 0, 0, 0, I turn on the tap, the relay to actually fill in the water. If it's 0, 0, 1, I actually turn off the tap, but I turn on the motor to spin forward. You know, so that is going to be the output circuitry. Okay, it also can be a combinational logic, or it can be a combination with analog circuit to read out from the flip-flops. Okay, so this is the power of actually remembering states. And now that if it is framed in this way, where you understand that each state has a meaning associated to it, then it becomes clear that you need to design the combinational logic here, the combinational logic here, the combinational logic here, in a way so that you can put in the new state here, okay, when it's time to change the state. So let's take the example that we are rinsing water. So okay, let's say I start with 0, 0, 1. 0, 0, 1 is the, sorry, not rinsing, we are filling up the washing machine with water. 0, 0, 1 is a condition where I'm filling up the washing machine with water. Let's say we start this, okay, is at 0, 0, 1, it's filling up water. So when do you actually change to stop the water and start rinsing? Okay, let's say that state, actually you want to go, that forward rinse is actually 0, 1, 1. So which means if you want to transition from filling up water to rinsing, you need to change this output. How do you change this output? You have to design a combinational logic here so that at a particular situation, you can change that output. Okay, so let me just erase this and I start to discuss conceptually how you would be able to design that output there. Okay, so I'm going to actually use a multiplexer, because a multiplexer basically will explain everything in a very intuitive way. Because a multiplexer is just a choice, okay? You actually have one output and another output here. It's just a choice. And here is your control signal. Okay, the input to the multiplexer is actually your control signal. These are actually your data. Okay, so I would like to highlight to you that typically in modern digital circuits, there you can conceptually identify what we call the data path. Data path, that is the data typically is something along this line. Okay, this is the data path. And you have something called your control path, which is basically the combinational logic to do control signals, the selection. Okay, all right. So what is the condition in which I need to switch from 0, 0, 1 to state 0, 1, 1? Okay, I need to see whether the water level, is it full or not? Okay, so I introduce a new input signal. Let's say this is coming from a sensor. It's called WL. If WL is 1, then this is full. If WL is 0, then this is not yet full. Okay, so the condition for me to switch to state 0, 1, 1 is first, I must be in the water filling stage, that is 0, 0, 1. Okay, so my condition is I have to be in state 0, 0, 1, which means that the washing machine is filling the water. And I must see that the water level is full, WL1. These are the two conditions. Then I will change this to state 0, 1, 1. So here I have a choice. I can either maintain it at state 0 or state 1. Okay, so this is 0, 0, 1. If I choose 0 here, it's still filling water. If I choose 1 here, it stop filling water, you move to rinse. So my combinational logic circuit here, this CP, is actually going to be an AND gate, right? Because I need two conditions to happen. I need WL, that is water level full to be full, and I need this to be state 001. Okay, 001, if I put it in sum of product form, basically I'm taking the output from the first flip-flop. This is 0. Let's call this Q0. Let's call this output here Q1. And let's call this output here Q2. Okay, I need Q0. I need it to be a NOT gate. Okay, so when it's 0, this is logic 1. Q1, I need it to be also 0. And Q2, I need it to be 1. This is the actual combinational logic that will drive this selection. Okay, so when it is not full, this will be 0. So 0 here, it will send this out here. It will send this output here like that. If it is not in the rinsing stage, then it will send also 0 out here to say, then it won't actually change this, like you'll just continue rinsing. Okay, but if it is in the rinsing stage and water level full, this will switch to, this multiplexer will then have logic 1 at this input. So it will now send in this value here. Okay, so this is the principle of changing the state. This is where there is a state machine. And in the diagram form, what we write here in this diagram, let's say this is state 0 is 001. That is filling up the water, and state 1 is the rinsing. I make this transition when WL equals 1. This is how we write the state transition. That is, if I'm in state 0, meaning it's 001, okay, and I see WL is 1, and I see WL is 1, I change to state 1, and state 1 is nothing else but this 0 here go to logic 1, and I implemented this as a multiplexer. Now I'm going to pause for a moment. Do you understand this?
Yep.
Great, Daniel. Alvin?
Yep.
Okay, great. So now you have got all you need to understand sequential state machines. Because a sequential state machine is nothing else but you have to figure out how many combinations of states or conditions do I need to represent in my circuit. And then you have to figure out how am I going to calculate or compute the state transitions. And then you have to do state assignment and all these. Okay, but basically you have a bunch of bits, and each bit you have, each combination of flip-flop bits is representing a state. Okay, and then you are taking a combination of the state, which is the values remembered from a previous calculation, in order to determine what is the next state, the next value set of values to remember. Okay, and then that gives you the way to actually design the digital circuitry at the input, which is just the combination logic. Because in digital circuits, everything, all the computation is done by combinational logic. The only complexity comes in is when you add in the flip-flops to remember. That allows you to remember past values to decide future values. And in the same way, you can actually design outputs, additional circuit, combination logic, taking these and all that. And I'd like to share with you, if you actually have a string of flip-flops like this, okay, and then combinational logic and all that, this is called a pipeline. This whole step is called a pipeline. Why? Because you compute something here. I change the color of the pen to yellow. You compute something here. The value is updated here at this point. Then the next clock cycle, you compute something here. And then next clock cycle, the value is updated here. So the value is as if it's flowing down a pipe of flip-flops. Okay, and this is exactly the pipeline that you've learned in computer architecture. It is the same thing. Okay, and what the pipeline is saying is that instead of doing all the computation steps, you have the instruction fetch, the instruction decode, the compute, right? So this first stage here, the combination logic is doing the fetch. The second stage here, this combination logic is doing the decode operation. The third stage here, the combination logic is doing the ALU operation. So this is the same thing. Okay, it's just to illustrate to you, to bring it together. A processor itself, a pipeline processor, is also a state machine. But because the number of states is very large. It's like, can say infinite large, because the number of states actually the sequence of instructions that you have. Each instruction actually is a state, right? And then each sequence of instruction also can be viewed as a state. So this is actually complicating things, right? To give us more power, more flexibility. And a computer is so useful because it is actually state machine. Because when you write each instruction, you think about each instruction, that's actually you're specifying the state sequence, right? Because instruction 1, instruction 2, instruction 3, that's a sequence. And each instruction also can be executed as a series of states, which is what you're doing in the pipeline, the fetch, the decode, the compute, the load, store, and things like that. So I'd like you to now be able to see in this grand framework what actually is a sequential state machine. Now, if you understand this makes it easier. I would recommend that now you can try that you understand this, you can try to design the state machines. It's good practice if you try to design maybe some examples from the Chu textbook. You try to design it directly using maybe multiplexers, and you don't actually have to have a one-stage multiplexer. Usually what I try to do is to make the concept simpler for students to grasp. I recommend you start your learning by assuming there are going to be 2 sets of multiplexers, 2 levels of multiplexers going into each flip-flop. Okay. The first set of multiplexers, the control signal is the state, the previous state. That means all the is going to be a combinational logic where the inputs are all the Q1, Q2, Q3. The second set of multiplexers, the second level, is going to be another combinational logic where the inputs are actually from like external inputs lah, like your WL and things like that lah. They are not from flip-flops. Okay, so I recommend doing this, and you can remember that to make it simpler for you, all you need to do is the multiplexer is basically a mapping table, right? It's not just 0 and 1. You can actually have a 2-bit multiplexer where this is 0, 0, this is 0, 1, this is 1, 0, this is 1, 1. Or you can have a 3-bit multiplexer where you actually have 8 conditions, or 4-bit where you have 16 conditions. And then you can start to imagine that this is just a digital number going in and it's just selecting the path. Okay, so this is a very easy way. Why? Because once you can design a multiplexer like that with the path, with the logic, you can easy convert the multiplexer into a NAND gate, a NOT gate, an OR gate. Okay, and multiplexers are what we call a complete logic. That means you can design any digital circuit with only multiplexers. Just the same that if I give you AND, OR, and NOT gate, you can design any digital circuit with just AND, OR, and NOT gate. Or if I just give you NAND gates and NOR gate, you can design any digital circuit with just NAND gates and NOR gates. So there's a complete set. But the multiplexer is particularly useful because it illustrates and it actually separates out this concept of having a control path that is a set of combinational logic that decides, that controls, right? And a data path, which is the set of combinational logic that actually calculates the data. Okay? And this is going to be important when you start doing things like like the memory and the processor, right? Because the processor, you have 2 things. You have circuits that's trying to change the state. Let's say going from fetch to decode to ALU, and then you have circuits that actually are manipulating data from your memory. Let's say you need to do register 1 plus register 2, or register 1 multiplied by register 2. So there are 2 distinct sets of control of logic, combinational logic, typically put behind flip-flops in every digital circuit. This concept you can find in any digital circuit. So your practice will actually be, you can look up digital circuits. An example would be from the Chu book. There are several examples like a video codec and all. You look it up, try to identify where is the control path, where is the data path. Okay, and I like to propose this method of designing circuit because you can straight away see where's the role of the flip-flops, where's the role of the combinational circuit. Now, I'm going to, the last step before I close the sequential state machine work is to actually draw the link. How is this linked to K-maps? And how is it linked to your way of actually designing? So if you look about it, you actually had your state transition table previously, right? Your thought here is your next state. So they'd always ask you to write your next state here, next state here. Sometimes they have like, let's say Q prime or things like that. But basically, here we have 3 next state, Q0, Q1, Q2. And then they actually have your inputs and they actually have you put your previous state. So when you design anything around a flip-flop and all that kind of stuff, you always are filling this state table where you have inputs previous state, next state. Now I'm going to make it very easy for you to see. The next state is colored yellow. The next state is actually the combinational output at this point. The previous state is colored blue. The previous state is the value that you remembered at the output of these flip-flops that you're putting into the circuit. So in the case here, going here. So the way I mentioned it, the previous state is actually going into this selection logic of the multiplexer. The inputs are just like IWL, that's the selection pin going to this. So very easy. Your K-map design previously is you're doing nothing else but just designing the combinational logic of this part here, where the next state is nothing else but the inputs to the D flip-flop. The previous state is nothing else but the output from the flip-flop, previous value remembered, going into this multiplexer input, and the inputs is going to this second level multiplexer input. It's exactly the same thing, except that with this intuitive approach, I'm teaching you how to use multiplexers to reason intuitively about this. But you can go ahead and apply this formalism, this K-map way of designing, and you still get a logic circuit like this, except it's maybe made from AND or NOT gate, but it does exactly the same thing as a multiplexer. The only problem with this approach is it doesn't scale up beyond 6 inputs. So if you have 4 flip-flops and 2 inputs, that's it, dead already. You cannot do beyond that. And beyond that, you actually go to Quine-McCluskey and all these kind of software-based method. Whereas the multiplexer method I am teaching you, you can reason about this very easily. And then later on, you can write Verilog code to actually implement these multiplexers very easily. And you rely on Verilog to convert the multiplexer into NAND and NOT gates. And even if you cannot, you don't even have a synthesizer to actually convert your multiplexer, you can actually hand convert this on your own. So this is a very fast way to build intuitive circuits that will implement your particular state machine. So the process of digital design is no longer deciding what are my AND or NOT gates. The process of digital design actually is deciding how many states are in my machine. What is the rules and the conditions in which I move from one state to another to implement the function of my digital circuit? What are the input conditions? What are the state conditions? Okay, and then can I actually imagine this? And now I'm going to draw one more parallel. Why this way of designing circuits is very easy. Okay, I'm actually going to, I actually need to type so that I can actually show you what these structures actually correspond to in Verilog. And you will see, oh, it's really straightforward, very easy to write the Verilog. So to give me a moment, let me switch to Microsoft Word. Okay, new, blank document. Let me go to share my screen, document 1 Word. Okay, let me first draw out our 3 flip-flops. Okay, let's just do 2 flip-flops lah. Then I will insert the combinational cloud. I'm just going to, in most kind of explanation, they draw it as a cloud like that. But you have to understand this is just nothing but a series of AND or NOT gates or a bunch of multiplexers going into that. Okay, so I have some inputs going here like that. Okay, like this. Okay, that's my flip-flop. Maybe I'll replace this with the multiplexer, the two-layer multiplexer that I shared with you, that concept. Okay, this one. So I have 1 layer multiplexer here. I have another layer multiplexer here. Okay, and of course, everything goes in like that. Of course, I've got input here. Insert shapes. I've got input here. And I've got input here. Okay, good. Now, if you see in your Verilog code, there's an always block. So the first step is you have to declare register. So let's say I declare a register 10, means a 2-bit register, and I call it Q. Register means you're declaring the outputs of a flip-flop. It's possible you can actually use registers to declare things like output of latches and all that, and even you can actually use registers for combinational logic and things like that. But I want to actually simplify this approach so that you don't have to, you can pick up all these like advanced things. They're not essential, but you can pick that up later. But if I give you a recipe that you can really apply, so that's the reason why I'm just saying that for now you can just assume that whenever you define a register, you're actually defining a flip-flop. Okay, so this is actually Q0 and Q1. Okay, why? Sorry, my word has frozen. Okay, I'm going to, okay, it's back on now. Insert. Sheet options. Right. So this is Q0. And this output here is Q1. So if you declare it like that, okay, register Q here is actually saying I want 2-bit flip-flop. So always at posh age clock, begin and, okay, Q, whatever here, this statement is actually saying, is actually specifying the input at this point. Okay, let me just fill that with gold as we said that. Okay, this statement here is actually specifying this Q. Okay, so let's say I call this max1. Let's say I just put some values like that. Let's see. Okay, and then I put in some, just put in some names lah, so it's a little bit easier to see. Hey, delay again. Sorry, ask your patience. I don't know why Word is acting up like that again. Okay, here we go. Okay, so I'm going to call this input A. Or this input B. Maybe I call A2 lah, and then this one called A1. And this one called A3. Oh my God, so frustrating.
Yeah, Microsoft Office is normally frustrating.
Thank you, Alvin, for the validation. I really need to get an alternative way to do this. I actually have a pen and a tablet, but it's a little bit old, so the Microsoft Teams doesn't run on that. And I could actually run this on BBB, but BBB I can't record it, and so you guys can't actually see the session. I mean, you're supposed to be able to record it, but I tested it last week and it's not recording. Okay, so let's have this here. Okay, let's call this A3. And I just give you an example here. Let's call this C1. C1 is a control signal. So I want you to see that I'm specifying Q, which is here. So let me change. Q here, if you do this, means you're specifying 2 bits at one. But if you just want to specify 1 bit, you can just do Q1 like that. So Q1 actually is this multiplexer structure. So I think you can do this. This is actually based on the condition C1. And if it's condition 1, it's actually the second multiplexer. Okay, so I'm going to code this part of the multiplexers as assign statements. I prefer to do it like that. So assign. So I'm going to call it wire, let's say M1, M2, and then of course I have input equals A1, A2, A3. Then of course I have some control signal, C1, C2. So I can do assign M1 equals like that. I'm going to do it in 2 ways. I'm just going to show you the assign version, and I'm going to. So assign the condition C1. Okay, the condition is C1. If it's logic 1, I go to M2. Logic 2, logic 0, I go to A2. So then this is M2, and this is A2, like that. Then I can assign M2. M2 will be dependent on C2. Okay, C2 is here. Then if it's then it's dependent on A1 and A3. If it's logic 1, it's A1. Sorry, this is A2. If it's logic 0, it's A3. Okay, and then I can just do assign Q1. This is M1. Okay, so this code, this part here, assign statement is purely specifying combinational logic. You write like this conditional statement with the question mark here. This is basically a multiplexer, whereas the C1 actually is at the input pin here. And again, C1 here is 1 bit, so you have 2 options, but you can actually stack. You know, you can actually have another set here, right? Another like C3, another multiplexer like A4 versus A5. You can actually concatenate this like that, right? Or if you actually want to, so this is one way of doing it. You separate out the combination logic. You just assign the last statement at the input of the flip-flops. This go one towards the state. This really separates things out, makes it easy to see. The other option is actually if you want to just code all of it inside the behavior part. So if you do an if else, this is also a multiplexer. So Q1 equals, so if C1, Q1 equals M2, M2. And then otherwise Q1 equals A2, right? And then you can break this down further, right? So because you see M2 goes through another multiplexer, okay? So instead of replace, now I will replace this one. Q1 to M2, I'll now do if C2, okay, then if C2, then of course Q1 equals, if C2 means it's A3, A3 and A1 at the bottom, A3, Q1, A1 at the bottom. Okay, so this is equivalent to this plus this. Or there's a third way, which is case statement. Case C1, C2. Okay, and Q1, if C1 is 0, C2 is 0. C1 is, if C1 is 0, you don't care about C2 C1 0 is A2. So you say this is A2. If C1 is 0, you don't care about C2 so this is also A2 again. If C1 is 1, C2 is 0, is A3 at the bottom here. Q1 1 equals A1. So and then you do your AND case here. So you see, these are 3 coding styles that will give you the same circuit. You can use a case statement, you can use an if-else statement, or you can use a combination of assignment with combinational logic here. Whichever you use doesn't matter, Verilog will just convert it into that form. But my favorite is actually the case statement because you look, This is nothing else but a multiplexer, right? This is the condition 0, 1, 2. This is the multiplexer inputs here, C1 and C2. And this is actually the mapping of the multiplexer output. So the case statement is really easy to map your actual design with the Verilog, and you can actually reason about your design very quickly. Okay. Okay. So if you understand that, all of Verilog should be really easy for you now. This is the purpose lah, to actually show you, and then you can actually go through. Okay, let me switch my screen to. You can actually go through. Oops, not this one. I don't want this one. You can actually go. Where is it? You can actually go through the EXA example, multiplexer example, counter example, and through the counter example, you can see the state machine. So if you get that, you understand that concept. Now it's time to talk about state SDRAM. Okay, so I'll just take a 1 minute just to check with you guys if you're okay. Can we proceed, or you want a short break? How is it going so far?
I think we can proceed, Doctor.
Okay, Daniel wants to
Yeah,
proceed.
we can proceed. Yeah.
Vino, so
Yeah, we can
okay.
proceed.
Okay, you're comfortable with what I've shared with you just now, huh? Because it's just boom. It's summarizing all your digital electronics undergraduate, the whole semester. It's summarized in that. Okay, so far okay, yeah? Okay, great. I'm going to proceed now. Now we're going to start a new page, which I'm going to have to give you a little bit of background on what is SDRAM and why do we care about SDRAM and how is that different from just regular DRAM. Okay. All right. I have uploaded a new video under module 3 here. So I recommend you just listen to this external video because he gives you a different approach to explaining DRAM and he goes in detail. So it's quite nice if you can follow that. But let me now motivate the DRAM question. Okay. Now let me share the whiteboard again. Share whiteboard. Okay. Now, do you see my whiteboard? Do you see my whiteboard?
Yeah, I can see.
Yes,
Doctor.
look, yeah.
Okay, so let's say this is DRAM. Okay, we start with the simplest DRAM circuit. What you usually have is you have address, okay, you have data, this is bidirectional, and then you have write, read. Okay, this is the bare minimum you need for a DRAM. And what is a DRAM? Is basically, you can think about it, is a bunch of boxes that can store bits. Okay. So in this particular, I'm going to actually say each box can store 1 bit. Okay. The address will actually tell you which box you are choosing. The data will actually tell you is where you actually put the value that you either want to store in the box or you want to take out from the box and put it on the data. And the write or read bar is actually telling you whether you want to take from the data line to put it into the box or take out from the box and put it on the data line. This is the most basic DRAM. That part is clear, right? Most basic. This is an unclocked DRAM. Okay. Is that okay? You can follow? Okay, I'm just going to go ahead lah until you stop me. Okay. All right. So what exactly is each of these box? In a DRAM, each box.
Sorry, doctor. I'm not sure, but I'm just seeing the old picture of the old whiteboard. I'm not seeing the DRAM.
Oh, okay. Thank you. Yeah. It's great, Cash. Good. Oh, thanks for that. Let me stop that. Okay, let me try again. Yeah, because is it not? Okay. Never mind. Let me draw it again now. Okay. No wonder you guys were confused because you're just still seeing the old board. Okay.
I think we're still seeing the whole body. I'm not sure why.
Okay,
How
you
about-
are still seeing the old board. Okay, let me.
Are you able to see the new board? I'm not
Oh
sure.
yes,
There's
I've been
something
drawing
wrong
on the board. Okay, yeah, something wrong. Let me unshare this first and then try again. Maybe because it's the app integration, because I'm actually opening up an app inside here. I'm not actually drawing on the
Oh, now,
Microsoft.
yeah.
Yeah, because it's much
Okay.
easier that way. Let me
Uh,
try again. Let me try again.
oh, you are drawing in a different app, is it? If that, you
No,
can share your screen.
Oh yeah, that's right. Okay lah, never mind lah. I'll just use it in the MS Teams since I've already deleted it. Okay, you see the whiteboard? You see my square box?
Yeah. Can see
Okay,
it.
so the most basic components of a DRAM, dynamic RAM, is this. You actually have address. You actually have data. And you actually have write, read bar. Meaning if it's logic 1 on this pin, you write. If it's logic 0 on this pin, you read. And DRAM is nothing else but, I mentioned, it's just a whole bunch of boxes here, okay? Where the address tells you which box you're going to use, and the data will actually be, if it's read, you're actually fetching from the box and you're putting it into the data line if it's read. And if it's write, you're actually taking from the data line, you're putting it on the each box. Okay, this is the most basic DRAM. And of course, as you can imagine, I'm going to explain a little bit the circuit behind it so that you can understand why we need to do what we are doing. Okay, why we need to do what we are doing. Okay. Okay, so now let's go a little bit deeper. Each of these box is literally a single capacitor. Okay, literally, it's just a single capacitor. Each box is a single capacitor. So what you're doing when you are storing the bit is you're actually charging the capacitor to logic 1, logic 0. And the capacitor actually is arranged in rows. And then, of course, there are rows of capacitors. Okay, so this is the second row of capacitor. Okay, and the challenge really is this. You probably don't want to use too much charge to store in a capacitor to store one bit. Okay, but because if you use too much charge, it takes too long to write a single bit, or it takes too long to read a single bit, and you are wasting a lot of energy. So these capacitors are actually really, really small. They're on the order of like femtofarad. Literally what it is actually, if you know your MOSFET structure, is literally the channel and the gate. Yeah, that's it. That kind of structure. Okay. So what happens is, because it's a capacitor, you will then worry. You say, oh, Dr. Ho, we can't store charge on capacitor for infinite duration, right? It will just leak and then the charge will disappear, and you'd be exactly right. And this is why all DRAM, any kind of DRAM, as long as there's a dynamic and a RAM in that, and if it's based on capacitors, you need to periodically pre-charge it, meaning that you need to strengthen the charge, because the charge is going to leak over time. Then it's actually a two-step process. You have to detect whether it's a logic 1 or logic 0 on the capacitor, right? And bear in mind the capacitor is leaking. So your issue is really how do you actually represent logic 1, because that's the one that it will leak towards 0, right? So you need to detect whether it's a logic 1, and if it's a logic 1, you need to charge it back. And this is done automatically. And what actually happens is there's also what we call columns reading out like that. Okay, columns. And these columns actually go to like data buffers, amplifiers, which we call actually the sense amplifiers. So the way you actually read DRAM, the circuit, I'm not going to go through too much the circuit, is you select the appropriate row. You select the appropriate row. So let's say your address, let's say here you actually see there are, okay, I'm going to assume that there are 4 capacitors in a row and 2 rows. Okay, so which means you have a total of 8 memory locations, correct? So this is the total capacity of memory is actually 8 bits. Each location can have 1 bit. So 8 bits meaning to address all 8 bits or 8 conditions, I need 3 bits in total, right? So my address space is actually going to be 3 bits. Okay, so my address, let's say I have out of the 3 bits. Okay, I have bit 1, bit 2, bit 3. So the way I partition my addresses is the first bit will choose, do I activate this row or do I activate this row? Okay. So if I choose one bit, I activate this row, all these capacitors will then go into this sense amplifier, and each sense amplifier will then magnify the charge on the capacitor. Because as you know, in digital circuits now, a logic 1 is maybe 1.1 volts and logic 0 is like 0 to 0.2 volts, right? But you don't store 1.1 and 0.0 volts on these capacitors. You store something like on the order of millivolts or less, okay, on this capacitor. So what happens is the small amount of charge is read to the sense amplifier. The amplifier will rapidly drive that to logic 1, which is 1.1 volts, or logic 0, which is 0 volts. Okay, so it will read out the entire row of capacitors, and after that there will be a bunch of multiplexers. Multiplexer 1 here, okay, and then there's another layer of multiplexers here, and this will be address bit number 2 and address bit number 3. Okay, and this is your output data line down there. Do you understand that? Okay, where is my screen again? Oh crap, that's gone already. Okay. Do you understand that now you can see the basic structure of a DRAM, that the address bit is like the address bits are actually telling you how to address each individual part of the DRAM, okay, and each bit is actually just a single capacitor, and part of the address bits will choose a row, and the whole row will be read out into the sense amplifier. And this sense amplifier, this whole row is also known as a row buffer, or it's also known as a DRAM page. They're the same thing, okay? And after this DRAM page is the remaining bits of the address is used to through a series of multiplexers to choose which particular bit gets stands out. This is the way that DRAM is read. Then after you read this, okay, because you've already read out the charge, and that the reads in DRAM are actually destructive. So you have two mechanisms. Like every time you read, you are cancelling the bit, and that bit has to be refreshed. And every time, if you leave the bit unread for a bunch of seconds, the bit will actually decay and disappear. So you have to pre-charge. So there are two operations that need to happen here. Okay, and they also take time too, because when you read an entire row, you're actually doing some charging to actually amplify at the buffer here, and then you're also doing some recharging of the bit line. So you can imagine this is the reason why DRAM is not exactly that fast to read, because the slow part is I have to actually do the row select, which is actually going to amplify and read out the entire row of capacitors into the buffer. And then it will also, after the readout to the buffer, there'll be some circuitry that also will restore the entire value of the row back into the capacitors. And there's also a selection of some multiplexers here, which will have some finite propagation delay. Okay, so this is DRAM. Okay, do you understand DRAM concept?
Yep.
Okay,
Yeah.
I'm moving on now. Okay, now it's going to get a little bit hairy. So this is basically a 3-bit address space, okay, and 1-bit data space DRAM. How do I get a DRAM with a 4-bit data, or let's say 8-bit data? Because now you see your modern DDR RAMs, there's always this like X8. X8 means the data width is actually 8 bits. So the way I get 8-bit is this 2D structure here. You see this 8 transistors, these 8 capacitors here. I have 8 of them like that. So I will have 8 bits like that. These 8 arrays, okay, so these 8 capacitors, I have 8 arrays of these 8 capacitors, 8 arrays here, okay, and each of them will share the same row select, and they'll share the same column select. Okay, column select is selecting one column. And then I read up the whole 8-bit data like that. Okay, this is called one bank. This is one DRAM bank. Okay, one DRAM bank will give you, if it's X8, 8 bits out. If it's X4, 4 bits out. That means 4 DRAM 1-bit arrays. If it's X16, means 16 bit out. This is one bank. Okay, this part is clear. Okay, now, what is this big deal of SDRAM? Because you notice I'm just telling you about DRAM, which is dynamic RAM. But today you have SDRAM, which is synchronous DRAM. Well, one of the main things is actually you see a clock here. Okay, right? And as I mentioned to you, this row select is actually an expensive process because you actually pre-charge and you actually buffer the entire row here. So if you actually have a situation where you need to address the bits continuously, like from this location, then the next location, then next location, next location, this is actually faster than selecting a bit here, then a bit here, then a bit here, and a bit here. Why? Because when you go from here, 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 you only need to select the row once. You do all that pre-charging of the amplifiers. The value is down here. Then subsequent bits, you're only changing the multiplexer. So you're only paying the price of the multiplexer propagation delay. Whereas if you're accessing bits downwards here, every bit access, you have to do row select, pre-charge, then you pay the multiplexer cost, and then the next one you pre-charge the next, you select the next row, and then you dump it out into the sense amplifier, the row buffers, and then you go through the multiplexer again. So there's a kind of asymmetry in memory access. So the key point of SDRAM is they're saying that, okay, you know, I have a certain amount of time that I will take to access, right? So if I want to access this bit followed by this bit, okay, this bit followed by this bit, is going to have like different time compared to, let's say, this bit and this bit. So the SDRAM sort of like, you know, let's just try to make all the time the same. So I first want to have my access happening on the clock. Why happening on clock? Because most modern circuits nowadays are clock-based circuits, synchronous circuits. Why? Because with pipelining tricks, you can actually run the faster part of the circuits, continue running, and then the slower parts of the circuit, you break them up into different clock cycles. That means you break them up into different portions of the pipeline, which is nothing else but saying that long combinational logic, you just chop it up and then you put flip-flops in between. That's pipelining, okay? So the reason you can do that is because you want to try to speed up and do more of the fast operation, and the slow operations, you break them up to multiple clock cycles. The second approach is they're trying to say that, you know, if I need to do this, okay, then instead of me changing the address lines, if I want to actually read all the bits on the same row, instead of me actually reading the address lines, I just put in the first location, and then internally I have another counter circuit that will change the address line so that it will change the lines itself internally. So I don't have to change the address pin. The circuit inside the DRAM does that. Why? Because the address pin, you can imagine, is going out through a big pin, right? So the pin compared to the actual wire within the circuit, the pin is of course much bigger, so much higher capacitance, much higher resistance. We will see this in more detail in VLSI class. So it will be actually slower and take more energy to actually charge and change the address pin. And you can actually change it slow because you need more energy to actually flip the bit to change the address bit. So if you do it internally, you can run this faster. And because it's done internally, the counter to actually increment the address pins is so close to the circuit, it can be very fast. You can talk about like gigahertz of speed at which you can update this. So the modern SDRAM, basically, they are actually trying to speed up the DRAM access by doing a couple of things. One, they allow you to actually clock the access, meaning that they are only going to allow you to see the output here at particular clocks. So you can imagine that what's happening is they put a whole bunch of flip-flops here at the output. The output is actually being put flip-flop. Actually, the flip-flops is here. It's at the sense amplifier side. Okay, the sense amplifiers are sort of flip-flops. They are not exactly flip-flops, but they function. You can think about their function as a flip-flop that does amplification. So they will remember the value, and once the value is there, you can just read them out using the clock. And then there's probably another flip-flop here, which is going to be able to read out and store the value of the multiplexer. Because then again, it's the same concept that the multiplexer just needs to, it can change, it can have different like propagation delay depending on which inputs are activated and things like that. Okay, So the second advantage is instead of asking you to change the address line every time, they allow you a strobe mode. This is called the strobe mode, where you just whatever address you specify, it will give you a sequence of data bits. This part, this part, this part, this part, and that's the strobe length, and that comes automatically at every clock edge. Okay, so your SDRAM is now an intelligent DRAM. For speed purposes, they allow you to increase the speed at which you read, especially if you have an open row. That is, if you're reading consecutive bits in a row. And now this is the reason why I had started giving you only a 1-bit DRAM, because it's easiest to think about how this works for a 1-bit array. Then you think about it, if it's a bank with an 8-bit data output, it's just the same thing, but you times by 8. And this is very interesting because this way of working is also what I like to call, it's called the bit slice concept. This is another important concept in digital design, where you worry about the design for 1 bit, and then if you want to make it into 16-bit, 32 bits, all that, you just repeat the same circuit 16 times, 32 times, and then you add maybe a little bit of control logic. That's it. So this is a very powerful concept for bit slicing, and this is how they actually design adders, comparators, and all that. This is how you can get 16-bit, 64-bit adders. So one example would be the carry, the adder carry thing. They design for 1-bit full adder, then they have the carry logic or the carry look ahead logic that helps you combine multiple adders. But basically, you are designing individual bits just well, and then you replicate the design to expand the bit width. And this is also building on the concept of data path, because in data path, you have this kind of concept. Control path, you don't have, right? Because control path, every bit, every signal has its own meaning, right? But in data path, you sometimes have data that is 1 bit, 2 bit, 4 bit, 8 bit, 16 bit. So if you design the data path for a single bit, it's straightforward for you to actually expand that design to do 8-bit, 16-bit, 32-bit later on. So this is the idea of bit slice design. So you should think about the DRAM to understand the concept for a 1-bit array, right? An array with only single-bit data values. You understand fully how the row and the column and the row buffer selection is done. Then you just multiply that 2D array times 8 or times 16 to get your byte or your whole data output, and that whole chunk, that whole module is called a bank. Okay, so we are doing all this, we are adding all this additional circuitry to the DRAM because we are trying to speed up how quickly we can access the DRAM. Okay, so that's why we call synchronous DRAM, and then it's in the way that you can actually access the values, like for, let's say, if you are accessing contiguously across the same row, you can access it very fast. The values will come out at every edge of the clock cycle, because at every edge of the clock cycle, you are changing the multiplexer value here. That's why if you look at the example design I gave you, there is a counter. There's a counter that is going into the multiplexer control logic, the control selection pin. And this is sort of interesting because when you see a counter now, you start to put things together. Oh, there's a sequential state machine, right? Yes, a counter is a sequential state machine. And this is why I'm asking you to separate the data path from the control path, because the array of the DRAM going into the sense amplifier, going to the multiplexer, this is the data path. And you see that the selection of the multiplexer is itself a separate circle called the control path, and the control path can have its own state machine, and the data path can have its own state machine. Okay, so this concept is quite important because it allows you to modularize and really combine your modules to build a big and complicated digital system. Okay, so the counter is basically a state machine generating the control signals so that the data path can actually feed out in a synchronous fashion. Okay, is the motivation and the reason behind as synchronous DRAM, is that clear? SDRAM.
Yep.
Okay, good. Now we're going to actually go a little bit more deep into this already, and then I'm going to give you the whole layout of what we intend to do for the rest of this semester and what I hope you can learn. Okay, so already we've covered already some basic but very fundamental, I wouldn't say it's basic, but these are key concepts and tools in digital systems design. You've seen control and data path. You've seen sequential state machine and how the multiplexer and flip-flop view of things allow you to really design very quickly and allow you to focus on the design itself, which is the concept. How do you assign the state meaning and all that kind of stuff? And now you've seen this concept of bit slicing, and now you understand why we are trying to add more circuitry around a DRAM to call it an SDRAM so that we can speed it up. Now, SDRAM is not used anymore today. Now you see DDR-RAM. Okay, DDR-RAM is even more complicated, but it uses many of the concepts of SDRAM with additional concepts. What happens in DDR-RAM is instead of the data output coming up only on the positive edge, you have double data rate. That means the data is coming out on the positive edge and the negative edge as well. Okay, and this one maybe they can do is because they use some fancy tricks. They don't just have one bank of memory. They actually have multiple banks of memory. Okay, and this is going to the idea of parallelization. I actually have multiple bank of memory. So you saw this one bank of memory. We said there are 8 bits in one array. So you times 8, so it's 8 bytes in one array. So one bank here has actually 8 bytes of storage. So if I needed a 64-byte storage, I can either implement a 64-byte bank, meaning I increase the address space per bank. That means I actually have, if 64, maybe I can do maybe 8 capacitors here and 8 rows, or I can do 16 capacitors and 4 rows, right? But instead of doing that, I can actually maintain my 8-byte bank, and I have 8 banks rather than larger banks. You understand? The reason being, I can then overlap the accesses. If I want to access row 1, row 2, row 3, row 4, okay, instead of storing all of them in the same bank, I store again all of them in 4 banks. Okay, so I can do the row access for the first bank, the second bank, the third bank, the fourth bank. I can do it simultaneously. Okay, and then once the thing comes up, it takes the same latency for it to come up. So I just serially choose between bank 1, bank 2, bank 3, bank 4. So now I've saved the time it takes for me. Instead of activating one row, then the next row, and then the next row, I activate 8 banks in total, but each bank I activate different row. Okay, and then the data can come out. And then they all read the data and store it in their row buffer. Then my multiplexer logic will just choose between bank 1, bank 2, bank 3, bank 4. So from your point of view, looking at the SDRAM, you don't know what's going on inside. You will just see, wow, the data is coming out very fast. But the trick here is instead of having one really large bank where I pay the penalty if I want to access different rows, I break it up into a set of smaller banks. Okay, why a set of smaller? Because I need the same capacity. I need 64 bytes of storage. But instead of having one big 64 byte, I break it into 8 bytes, or I can break it into 16 4 bytes. You know, there's a trade-off, or I can do 232 bytes. You know, it's a trade-off, right? There's some design questions to answer, but the key idea here is for parallelization, I want to have multiple units of operating units where I can start the operation in parallel. Okay, and then they finish their operation, and then I can collect all the operation result, and it looks as if I have a very fast single bank, but actually it's not. I'm giving you the illusion of speed because I'm operating in parallel. Okay, so why I'm mentioning this, because modern DDR and even SDRAM itself, you typically don't have one bank. Okay, what actually you have is you have your DIMM. Okay, this is called DIMM, and DIMM stands for Dual Inline Memory Module. And each DIMM actually you have a bunch of chips. Let's say this DIMM has 4 chips here, right? And you actually have chips on the front side and the back side. Okay, right. Each chip will have multiple banks. Okay, one chip will have multiple banks. Okay, so you remember you have times 8 data out from one bank. So maybe this chip has 4 banks. So you can imagine this 3-dimensional kotak here, this 3-dimensional cuboid here. There are 4 of them in one chip. So one chip can access 4 parallel rows at one time to speed things up. Okay. And in order to get, let's say your modern memory now, your computers don't use 8-bit data words, they use 32-bit, but now actually 64-bit is common. Okay. So if 4 chips, I have 4 banks in one chip. If I combine these 4 chips here, these 4 chips, if you've got 8-bit, 4 of them will give me 32-bit data word. Okay. So combining 4 chips together to get a 32-bit data word, that is called a rank, R-A-N-K. K. Okay, so you can think of rank as expanding the 2D array here to get more data words. Okay, it's the same thing, but except that a bank is the extension in this dimension. For a bank is within the chip, and for rank it is you are multiplying more chips, right? Because off-chip accessors are more expensive than on-chip accessors and things like that. And the goal of this is we don't want to make too large a DRAM, because you cannot make too large a DRAM. Because why? Because as I mentioned to you, you're activating one whole row. So if you imagine you've got four capacitors sitting on one row versus 64 versus 2048, which one will be faster to activate? Of course, the 4-bit one, right? Because it has less capacitance to read out and it's faster. So the larger your DRAM array, the slower the array it is. So there's some kind of like intermediate sweet spot of the size of the DRAM array, the size of the DRAM bank, and then you have to use this multi-bank within the chip, multiple chips to form a rank, and multiple ranks to actually get your memory to have large capacity and large data width. And that's what we are going to be studying. That was the philosophy of this class. So you see the bank approach ready. Then there's this issue now. We're talking, okay, you know, we went from a very simple concept, address, data, read, write, right? Very simple, no even have clock. Now all of a sudden you have this stroke where you only give the base address and then all the data is being read out from the same column out into the multiplexers in a sequence according to some clock. So there's some clocking logic that needs to happen, okay? And you have to read out over the whole bank. But now you also have within the same chip, you have multiple banks, okay? And different banks will be covering different part of the address space, okay? So you need to have some additional state machine and logic to figure out, okay, I have, like, let's say, requests for 5 different memory addresses or 10 different memory addresses that the CPU wants. How am I going to activate the appropriate banks? So that is the later part of the course where we will study about the interconnect, which is hopefully we can cover crossbar. That is basically this idea of routers. How do you actually choose? Crossbar is an extension of multiplexers. Actually, you can implement a crossbar with multiplexers, but this is trying to actually study that problem in more detail. How do you actually implement a crossbar switch to actually choose the outputs and the inputs to the bank? How do you actually develop the state machine and the scheduling logic so that you can choose to forward the instruction? The instruction here is I'm requesting a particular address and I actually have some data that I want to write or read. So you have a bunch of these now and it's going to 4 different units. That means 4 different banks, right? So how do you set up the digital circuit such that you can send the appropriate request to the appropriate bank and send the output in the appropriate order? So there needs to be some decoding logic that you can actually store the instructions. Okay, the instruction is nothing else but what is the address, the data, and the read-write operation that you want. So if it's a write operation, you also need the data. If it's a read operation, you don't need. Okay, so this is your command. So now modern SDRAM, DDR-RAM, there's actually, you can think about it, it's almost like there's a processor within the DRAM itself. Why? Because it has to decide, you have these commands coming in, this instruction coming in, which is an instruction to basically read or write a particular address, and then it's coming, a series of instructions are coming in. That means a series of different addresses with different read and write instruction, and they have to be sent to the appropriate bank on the chip. Okay, and we can make it a bit more complicated by also getting you to design this for ranks and multiple ranks. But I think maybe given the time and given your pace, maybe we will just forget about the rank idea and we just focus on multi-bank. That might be okay. So that, okay, let me now go back to our Ulan side and try to discuss what is the sequence of operations. So practical module 1 is just more of like getting you familiar with Verilog, writing test bench, and doing simulation. If you've understood really well the state machine, sequential state machine design process earlier today, this one should be no problem and you should be able to design. You just need to practice a little bit. Maybe you can look at the Chu textbook examples here from chapter 1, 2, 3, 4. You pick 3 or 4, just get yourself familiar with design. But that is actually more of like the introductory prerequisite. The first part here will be the XDRAM controller with state machine. This first assignment is actually testing you whether you really can design state machines according to the methodology I give you, because that gives you an easy way to do it. And let's take a quick look at this assignment so I can explain to you why and the motivation, and hopefully you can then set to work on it. Okay, this is the assignment, okay, and I've given you a series of configuration, okay. 64 megabits, okay, times 4 means this is a 4-word, a 4-bit word, okay. That means if you will go to look back at that 3D box, okay, that is one bank. So I'd like you to have the association, the 3D box is one bank. I'm trying to actually draw it out for you. So it's something for you to visualize. Insert, where's my drawing? Shapes, all right. There we go. Where's the 3D box? No 3D box? Oh, okay, there it is. Okay, so you have a 3D box here. You remember row is actually horizontal. Vertical is actually column, okay, and both of that is address. And the box depth, okay, that is times 4 bits. So 64 megabits, meaning that this box actually has 64 megabit locations. Okay, that's what it means. All right. So this is an indirect way of giving you the size of the address. So you have to back out and calculate how many bits of the address line actually for one bank. So there are 8192 rows. I told you there are 8192 rows, and there are 4 banks, and then there are 2048 columns. Okay, so I've already given you the instruction there already. All right. And I've gone a step further. I've given you a bunch of commands. Okay, these are typical SDRAM commands. What are they? So T command is actually the time it takes to actually decode the instruction. Okay, this whether is it there are about 5 types of instructions that you can actually perform in a modern SDRAM. TRAS is actually to do that row select. That is, you actually select one row, it goes to the sense amplifier, the row buffer, and then it charges all the way out and amplifies. So this is the complete time it takes to actually, when you put the address, is actually to activate the entire row. TCAS is the time it takes to select from the row. If everything is in the row buffer, the time it takes to access and select one bit from the row buffer, okay, to actually do the complete read. And TCCD is the time is actually to write one bit into the sense amplifier. So because memory, there are two general operations, right? There's reading and there's writing. And reading and writing requires row selection, column selection, but of course the timing is also different, right? Like the time it takes to read from a column is different from the time it takes to write from a column, more or less. That's why we separate out the time. And T-burst is actually the time for you to read out a consecutive series of columns. Remember, we said that since we paid the price for row access, you can actually read either one bit or multiple bits from along that column. And again, multiple bits means multiple boxes within the DRAM. Okay. And T-write is actually the time it takes to store a column of value sorry, just now the TCAS is read, T-write is actually writing. TCCD is actually the time it takes from the output of the multiplexer to go to the data bus. Okay. And TRP is the time it takes to pre-charge this. And this pre-charge operation I mentioned to you has to be done on every single DRAM bit. Why? Because if you don't do it, it will the charge will disappear and then your data is corrupted. And there is a timing that is required for TRP. You actually have to recharge the entire row. So recharge is done row by row. Every time you want to recharge, you just charge all the capacitors in one row. Okay, so one recharge operation must be the complete DRAM must be recharged every 64 milliseconds in a modern process. Therefore, if you break this up, you want to actually have uniform, you actually have to recharge each row every 7.8 microseconds. Okay, for this one, right? Okay, I'm going through this all because I'm giving you the real world details, because this is actually data taken from, is actually realistic timing from a DDR3 1600 megahertz DRAM, SDRAM technology running with a 200 megahertz clock frequency. So these are sort of realistic clock values and sort of realistic timing. But the key point here is this, okay? we are talking about read and write operations to your SDRAM here. Okay, and a read and write operation is not a single operation. It is a sequence of states. Okay, so the complexity here, why I want you to implement this state machine is because you will be there will be a read instruction and there will be some write instruction coming in. That's a high level instruction. So the read can be, say, I read one particular location, or I want to read an entire row with a particular size. Let's say eight column row or 16 columns in a row. That's the stroke activity, right? So you have that high level command, and that high level command, the decode will actually break it down into a series of smaller states. Okay, and these are the states that I already have defined for you here, this state transition diagram. And we are going to start implementing the logic that allows you to manage the read and write as a sequence of small states. So asking you to complete this state transition diagram is saying that if, let's say, I want to read a single column, okay, what is the state series of state transition to read a single column? So you always start at at idle. So first you have to do a row access. Row access would be, oh sorry, I've already done this for you already. Read, yeah, I've already done this for you already. Right. So read basically is a random read. That means you're just reading one location. Read is a continuous read. That means you're reading a sequence of locations now. Okay, so the sequence of actually read is basically you have to do a refresh. Okay, that is you do a selection of the row followed by a random read operation. Okay, so the first operation, let's say you are doing just reading a one sequence, you start from idle, you have to do a random refresh, okay, and then you have to do a random read, then you go back to idle. Okay, then if you need to, then you have to do the next possible instruction, which is basically I'm doing a contiguous read. So it will be a random refresh, contiguous read, idle. Okay, that is your three step. Then you actually have to do a random write. Random write is a random refresh, random write, idle. Okay, and in between all of these, periodically there has to be a counter that you actually periodically go to refresh. Oh, sorry guys. I'm a little mixed up here already. Can we rewind back? Can we rewind back? Sorry, yeah. Sorry, I'm a little mixed up with my own definitions here already. Let me reset this. Let me reset this. Okay. Here in the random read operation, this is the timing defined of certain operation, and this is the random read. I've already actually combined this for you already. The random read operation consists of decoding the command, row access, column access, column burst, and precharge operation. Random write operation consists of command decode, row access, burst, and write operation, and precharge. Okay, a contiguous read. This assumes that the row is already open. Is only a column access and a burst, and the continuous write again is the burst and then the write access time. And the random refresh is basically this refresh is actually the charging that you need to actually do on the DRAM to actually refresh the value so that it doesn't decay and leak and get corrupted. So there are two types of refresh. One is the row is not really open, so you actually have to open the row and select the row. The second is you are doing the refresh because that row is already open, so you want to save some time, right? You can actually save something like almost 35 nanoseconds. And if you're doing this over 10 rows or 100 rows, you're saying like 3 microseconds really, that kind of thing. Okay. So what I'm doing basically, why this is looking so complicated is this. Within one operation, let's say read, you already have a sequence of more elementary operations. The elementary operations are actually this one: row access, column read, column write, pre-charge, and refresh. Refresh is actually restoring the charge value to prevent corruption. Pre-charge is actually after you've read things out, you have to put back the value into the capacitors, right? Because remember, reading out the sense amplifier actually destroys the value in the DRAM. So you have to restore it back from the sense amplifier. So that is the pre-charge step, okay? So I've done something which is I try to simplify it, which is I try to combine a bunch of these basic commands into composite commands lah, called read, write, C write, because the composite commands are more intuitive lah. That would be the commands that you actually send from a processor lah, right? But I'm combining it with basic DRAM commands and giving you a timing for that. And what I'm asking you to do is to do the state transition diagram for all these composite commands, right? So the read will basically be from idle you can go to read, then you come back. Then from idle you can go to C write, then you come back. Either you can go to random write and then you come back. But you need to recognize that you cannot jump directly to C write. You must have done an read or an write of that same row before you can go to C write or C read. Because why? The contiguous read and contiguous write depends on you opening that row first. Okay, so that is what you have to, the one step that you have to finish up this diagram for. And then the next step is how do you actually design the state transition diagram such that you can actually refresh periodically under this constraint every 7.8 microseconds lah. So typically you would actually need to design another like counter lah, that basically keeps track of each row. So you can do it a dumb way, which is you just do a counter, and then that counter after every 7.8 microseconds, it will increment the row, and then it will request you to transition from idle to ref to refresh. And then if you want to build it more intelligently, you can actually keep track of what are the open rows at the moment, and then if you see if that row has not been refreshed, you can actually just directly refresh that row first and things like that. So this is an open-ended problem. You can do it the simple way, or you can actually try to test your skills to do it a more difficult way. Okay, and I'm asking you to modify the design because in the Verilog code I gave you, I only did I think I only did a burst, a fixed burst, right? But what I mean by modify the design is that you introduce some additional logic so that you can actually change the size of the burst. This is maybe you can implement a new register in the design where the burst depends on the value in the register, and as part of the command decoding in a later stage, we can actually update this register so you can change the burst mode. Okay. So this is this first assignment. The goal of this assignment again is to throw in some real world complexity. As you can see, we have combined two levels of state machine, but I'm only asking you to design the state machine at one level, which is at this composite command. There is another level here, which all of this, which the goal was actually to do in a later assignment, right? Because this part here actually will be trying to address it in the pipeline design stage. So instead of actually breaking it up as, you can break it up as a sequence of states. Then once you break it up as a sequence of states, you can actually break it up as a pipeline. Because the idea is something like this. If you did a random read, you can do all this in one sequence, but you can do it in one operation. That means there's no flip-flops in between. You just wait this amount of time, which is what I'm getting you to do here, right? But later on, we're going to break up all these operations into sub-clock cycles and pipeline them, right? So that you can actually start, let's say, a new command. Let's say you're still processing the random read, right? Once it's going to the row access, you can actually start decoding the command of random write. So this actually improves the throughput of the design of the circuit, right? Okay, at this point, I've spoken quite a lot. I'd actually like to take a pause and ask you, did you understand all I shared just now? Do you understand, is it clear what is the goal of the assignment and what you need to do at this point?
Hi, Doctor. Regarding the state machines, right? Because I thought that the state machines, I mean, for this, right? This part, yeah. Actually, right. I thought for this, right? It's like it's not like just now you mentioned that if you want to read from ideal, you go to refresh, then you go to row read, and then column read, and then so this tab that's a single operation. So what I was thinking was is like probably there is a mixed operation of the DRAM. So at the same time, you need to include refresh all the time, right? Like it has to refresh every 64 microseconds, if I'm not mistaken. So
Correct.
yeah, so basically the confusion there was the ref and the refo. So I'm not sure which one to include as a the constant refresh rate, the 64 microseconds one.
Okay, okay, good, Alvin. I think you've shared some things that you understood and some part of your confusion. Okay, let me try to readdress your confusion lah. Okay, there actually is another state machine that can be designed for within one RRID, like to do the command decode, the row access, column access. There is another state machine, but for this assignment, I'm not requiring you to design that state machine. I'm just requiring you to assume that state machine already exists. Okay, because the goal of this assignment also is to illustrate to you another concept, which is nested state machines. That is, within one state, you can actually be running another state machine within one state, right? So let's say within the C read, if you're actually in the random read state, you can actually have one control logic, one state machine that actually controls, okay, I'm now in R read state, but once you're in R read state, you are running another state machine in R read state, right? And that state machine does not have to be complete before you go back to another high level state, right? So the goal of this assignment actually is to, by experience, introduce you to the concept of nested state machine. Now, what you're required to do, as I mentioned, would be to actually fill up this basic state machine, because the key problem, the first problem I've given you is that the state transitions are not all single clock cycles. They're actually different clock cycles. So that's the first basic step you have to mention, right? Because if you just draw a line here like that, that means every clock cycle you go back and forth. But what I'm essentially asking you to do is you have to count clock cycles within the state, right?
Okay.
All right. So if you count clock cycles within the state, you're already designing a state machine within the state, right? But it's an easier concept for you to think about it, right? Because in your undergraduate, you just draw single lines, right? And that means that the transition happens every clock. But what I'm trying to get you to recognize is that that does not need to be the case, right? You need to be able to say, let's say from idle, you move to RRID. RRID, you need to stay in RRID for 14 clock cycles. Then only you come back to idle. Then you may actually go to RWrite, right? Then you go to RWrite in one clock cycle. Then you need to stay 16. You cannot RWrite then straight away go back, right? Because the write operation needs to complete, right? And while the write operation is not completed, you cannot start the refresh operation because you are using the bank.
Yeah.
You understand? So that is the complexity, that if you can actually handle the number of uncertain, the different number of counts within each state, if you can handle that, the next level of complexity is how do you manage the fact that you need to revisit ref state every 7.8 microseconds. But supposing at the 7.79 microsecond, you start an RWrite state. At 7.8 microsecond, you cannot simply jump and go to ref. You have to finish your RWrite operation, otherwise you will corrupt it. And if you don't finish it and you go to RF, then how are you going to restart it? So that is the open-ended design. How do you do that, right? And then I'm only giving you the ref O operation just in case you wanted to be fancy, that suppose you've done an RRID, right? And then something happens that RRID is actually the same row that you need to do the ref. So instead of going for ref, you go for ref O. So it speeds things up. So this is a final point. It's more like for extra credit, because in reality, there's a sequence of competency you need to build. The first sequence of competency is, can you actually do this different number of clock cycles within each state? Because then this already lets me know you already have some competency to do nested state machine. Then later on, I can actually start putting the pipeline, because state machine and pipelines are actually two sides, flip sides of the same coin, right? You can look at the pipeline, actually it's a state machine, but it's a state machine that has been rolled out spatially, not just temporally. Right, that's what it is. Is linked. It's linked, right? So this is actually building you up towards that. So the next step will be, how do you handle this ref and ref O? Then if you can do that, then you have met the design goals for this, and then the T-bus. And then later on in the second assignment supposed to send out to you guys, which is that the bit slice. Is after the bit slice thing. Bit slice thing is actually more of like getting you guys to combine everything into, put in the multiplexers to combine it so that it becomes a bank. Okay, so that one is also relatively simple. It's just so that you can actually make sure you understand the read-write pins and all that. In practical module 4, this is where we're going to start. I'm going to give you a FIFO code, and then you're going to start looking at how you can actually decode the instructions. What are these instructions going to be? these instructions are going to be C read, R read, C write, R write, and all these things. Ref, we won't have, because ref has to come from the internal SDRAM controller. So ref is something that at some point internally you have to somehow figure out, after I do this right, I'm not going to accept any more transactions. I'm going to pause the transactions, but I'm going to be able to do my refresh first. Then only I go back and fetch the transaction. So that is why you need this high-level state transition diagram. Then later on, after you do this, we're going to look at the instruction decoding flow, which is basically the instructions, this C write, R read, that is going to actually select these state machines, right? Because now I'm just assuming that there is some kind of command that allows this transition to happen. And you should also do that. You should also have maybe like a command input equals R read or command equals C write, right? That's fine, because then you understand that this is the necessary condition to transition. Because you notice in my assignment, I've not told you what are the conditions on transition, and I've not told you what are the input signals that you require to do that transition. The reason is because this is an open-ended design. I want you to basically figure out what exactly do you need to actually get this design done, right? Because this is mimicking a real-world design operation. Okay, so it's complicated on multiple levels, but if you get it done, you will really learn a lot. Like, you have so much confidence to be able to design this, and then at the end of the day, you also have to put in the test bench, and you have to also just draw the schematic so that you understand what does this circuit actually look like, instead of just writing Verilog code. So because you need to understand that Verilog code is just not coding. You're actually giving the specifications for a circuit. You might as well be drawing the circuit diagram, but instead of drawing it, you draw in Verilog code. You write Verilog code. That's why we went through the sequential state machine this morning, is to show you that this is actually how I think about it, and you can do this design very quickly if you follow that series of steps, and then you spend most of your time worrying about the design rather than about how do I actually get the gates out, which is where it should be, because there's all these high-level issues. Okay, right. So if this assignment is clear, it's probably good if you can finish this ASAP, because we are running quite late already. It looks like I'm not even confident I can actually go through all of the work that we actually intended. So I'm going to go to the ULearn X, and then now I'm going to actually start talking about what you guys can practically achieve. So assignment 2, you must finish this. What I want to do is I'll be coming up soon with this load store architecture, which is basically how do you actually receive and decode instructions. Because as you start to be able to realize with our discussion, the instructions are going to come in anytime and every time. The CPU is not going to wait for you to do your refresh cycles, the SDRAM to wait, right? It's up to the SDRAM to actually manage to actually remember I have this instruction waiting, or this 5 instruction. I need to do them in my time, but I need to also do my own housekeeping refresh operation. So I need to manage that. So the next module would actually be showing you an example of the load store, and then maybe get you to like modify the code to improve its performance, things like that. And then I would really like to do the pipeline part, because that's important. That is actually breaking down, let's say in the random read, I'm actually going to start breaking down how do you actually design and break up into like row access, column access work, and things like that. Okay. Ideally, we can get to the multi-bank parallelization, because this would be the culmination where you actually, minimum, you have 2 banks. You actually build a crossbar interconnect, which is nothing else but a multiplexer with some control signal. And the more importantly is the scheduling. That is, if you receive one instruction, is it being sent to bank 1 or bank 2, right? And then if you're sending it to bank 1, how quickly can you fetch the next instruction and decide whether you are sending it to bank 2? And can you be a bit more intelligent? You do look ahead, that if you have 3 instructions going to bank 1, and then can you send the first one to bank 1, then you read up till you get the next instruction to bank 2, and then you send the 4th instruction to bank 2, and then after bank 1 finish, you send the 2nd instruction back to bank 1. So this is a scheduling problem. So in modern digital design nowadays, most of your work actually is in interconnects, scheduling, synchronization. you are no longer designing in the old days like you're designing the adder and all this, because Verilog and the synthesizer can do all this for you. And besides, 20 years, companies in digital design, they have 20 years worth of example designs of adders and all these kind of things. So they know how to build this very well. But most of the modern work is in bringing together the systems to handle parallel systems, playing tricks with pipelining so that I can actually improve my design. Why? Because sometimes you want to go faster, you actually need to break it up into more pipeline stage so that, because pipeline is also another strategy that you can actually use different resources at different times. So it's a parallelization strategy as well. Yeah. So these are the main concepts I want to cover. But it really depends on how quickly you can finish the assignments. And I also don't really want to overload you, because it's no point we go all the way to the parallelization, but you are not even firm on the bit slicing or on the state machine concept, right? So I think what is realistic is maybe we can at most touch until module 5. We might not be able to go to multi-bank parallelization, but if you guys can actually submit the assignments quickly, like, just get it done quickly and submit to me, then I'll know that you're actually keeping pace and we can actually do more. But as it is, I'm thinking at most I will just add another 2 more modules, which is the load store and the pipeline, and then that will be it for this semester. Because if you think about it, you have 2 outstanding assignments due to me, module 2 and module 3, and you have only roughly about 4 more weeks to go only. And then if I want to give you another 2 more assignments, I'm not even sure if you guys can manage it. So it's a good time now to get your feedback. What do you think about this process, and how would you like to do it?
We'll try to submit the assignment first, and then we will see how we can continue the course for module 4, 5, and then if we manage to go to 6. So it's all based on assignments, right, Doctor?
Yes. This course, actually, most of the learning is experiential learning. So you see, I don't give you many videos. What I can do is we can have more interactive session. And if you all can manage it, I'm willing to also do sessions on weekday nights to give you all more guidance on that. Because this course, I think, it's much better to actually give you example code. Then we discuss the main concept, and then you go ahead and you try and you work on it and you modify the example code. So you see how it's done in practice with the example code, and then you see how you can actually apply this.
Okay. All right.
Okay.
So how will be the final exams be?
Great. I also wanted to talk about that. The first thing I want to ask is, can you both give me an agreed date? We can discuss 5 minutes now. When is the best weekend we can schedule all your final exams? Actually, it's your extended assignment. Is done over a 24-hour period. This semester, there's no exam, so you don't come to UTP. We'll be giving you an extended assignment, which is basically a hands-on open problem. You can refer to any book and any resource. You have to get it done. You have to submit it online at the UlearnX platform within 24 hours. You cannot be 24 hours, 1 minute. So I request it's better you submit like a little bit earlier. Okay. So you have 24 hours to work on it. It's going to be hands-on, and I'm actually still designing, so I would be good to get your feedback. Is it safe to say that can we agree that module 2, module 3, and maybe module 4, this one must complete in this semester? Can you all commit the time to finish at least these 3 assignments, module 2, module 3, module 4? Is that okay?
Yeah, I'm okay with that.
Okay, how about you, Alvin?
Yep, I'm okay.
Okay, so because I have my doubts whether we can reach module 5. So I'm not sure whether I want to include module 5 into the final exam. Would you like module 5 to be in the final exam? Extended assignment, not exam.
Yeah, I think extended assignment should be okay. How about you, Ais? I'm not sure.
Yeah, I agree with you, Alvin.
Okay, so I'm going to include all 5 modules. The parallelization one we stay and see, but the pipelining can be in the extended assignment. Okay,
Yes.
so we're going to try to really go for that. That's your commitment, and my commitment also to really push harder to get that done. Very good.
Okay.
Now let's look at the exam dates that you can possibly make. So what I'm going to try to do is, I guess you guys don't want like overlapping, right? If you're doing one exam, you actually don't want to be doing the second exam at the same 24-hour period, right?
Yeah.
Yeah.
Okay, so you only, I would assume you only have the weekends available to actually work on the exam, right?
Yep.
Yeah.
So would you prefer it to be scheduled, let's say, first week Saturday, second week Saturday, third week Saturday? Because you all have 3 courses, right? Not mistaken, DSD, VLSI, and image processing, right?
Yes.
Yeah.
But if image processing, we don't have exam. If I'm not mistaken, we have assignments.
No,
So
all the courses this semester you have extended assignment is 24 hours. So let me distinguish.
okay, I see. Okay.
There's this course assignments, okay, that is module 2, module 3, module 4, module 5 that I'm giving you. I will give you 60% of your grade from these course assignments. And then there is, instead of the final exam, there is something we call the extended assignment. Let's just call it EA lah. EA. The EA, you have 24 hours to complete it on a scheduled date. That takes the place of final exam. So what I'm asking is the EA, you all typically will have just the weekend to work on it, right? You don't actually want me to give you to schedule an EA on the weekday, do you?
No. I think weekend will be better.
Okay, so the next question will be, do you prefer, because there are 3 courses that you're taking. Anybody taking 4 this semester?
I think I'm taking the research methodology. So
Methodology. That has another EA lah on its own.
yeah.
Okay,
Yeah.
so what I'm asking is, I can request, because now it's early enough, but we're actually on the edge already. I have to actually make my request now in order to give you a suitable time. If we can lock the dates, do you want EA, let's say Saturday, then Sunday, 1 EA, Saturday, 1 EA, followed by Sunday, 1 EA, then another Saturday, 1 EA, and then the next Sunday, 1 EA? Or do you want it to be Saturday, then the next Saturday, then the third Saturday?
Saturday, right?
You
think
prefer
Saturday,
to
yeah.
space it out as much as possible lah. Okay, over
Yes.
3 consecutive Saturdays lah. Okay.
Yeah.
Okay. Okay, let's quickly take a look at the exam calendar. Then I'll let you off for lunch. After that, then we'll meet again at 2 for the other course. Let's just quickly take a look at the exam calendar. Because I want to actually lock in the Saturdays so that you all can lock in your dates to, you can make your work arrangements lah. Academic calendar. Okay. Extended assignments. Okay. This is for January. May. Exam week is from 26 October to this is foundation. Undergraduate extended amount from. Okay, no. I'm looking for. Undergraduate May. 20 April to 8 May. Okay, exam week is from 26 August to 5th September. Oh wow, it's only 11 days. I don't even know if we have 25th August to 5th September. Oh dear, we only have 2 weekends. Yeah, so there's not much choice really. So it's basically 29 August, 30th August, and 5th September only. 5th September. So there are only 3 days really. Is it okay if you can allocate 1 extra day, Alvin? Because you have only 3 days here.
I mean on the weekends?
Yeah, these are the 3 weekends, 29th, 30th, and 5th September. Because the exam duration is between the 26th to 5th of.
Yeah, I think I'm okay.
You're okay. So
Yes.
I will request for 1 exam on the 29th, 1 exam on the 30th, and 1 exam on the 5th. All right?
Okay.
If research methodology, maybe we can try to request on a Saturday also lah. Which Saturday would you prefer it to be on? For those of you taking. So you'll be actually overlapping papers lah, but I think it should be okay lah.
So it's August. August 29, 30, and 5th.
5th September.
Okay, so
I mean, if you like, I can actually request for 6th September lah. Just for you guys. I think I can request 6th September as well lah. Okay lah. Let me do that lah. Let me also request a 6th September. I think they can extend it by one more day for you guys. So 4 courses. There is DSD, VLSI, image processing, and research methodology. Anyone taking any other course?
No.
No, okay. So I'm going to request research methodology on the first date lah, 29 August. Which course you want on 30th August? Out of DSD, VLSI, image processing.
VLSI.
You want VLSI on the 30th, Okay.
Yeah.
So RM, VLSI. Okay, and then image processing and DSD, they will just decide lah between 5th and 6th. I'll let them decide lah. Okay, good. We've sorted that out. That's great. So maybe the one last would be can you actually give me the dates you want to have another set of meetings? If we can actually lock the dates that you want to have these virtual discussions now, will be great lah.
Yeah.
Okay, do you want to have another one next weekend, or do you want to have something also on the weekday nights? Maybe you can just suggest some dates and times. I would say mandatory, we need another 2 more sessions, but if you need more, just let me know. Just propose how many sessions you want and what dates and times you're willing to go for. Maybe I'll give you a little bit of time to think about that. Maybe by end of today, if you can email that to me, that would be great.
Okay.
Instead of email, sorry. Instead of email, can you actually go to the ULearnX site? ULearnX site, there is actually a chat. If you go all the way on the top of the page, there's actually a chat there that is scheduling interactive sessions. So you just type in your dates and all that in that chat session, so that both of you can also see each other's dates, and then I'll just respond there and then we figure out. So the next action item by end of today, suggest to me how many sessions you want, what dates, what times, and then we'll work around and find the best arrangement for everyone. Okay.
Okay, great.
Okay. Since we are ended about half an hour later, do you want to start half an hour later, or can you guys start at 2 p.m. sharp later?
We start at 2, right?
You start at 2, Okay, very good. Alvin, you're okay with 2? Okay?
Yeah,
all right.
yeah.
All right, guys, I'll see you later at 2. Also on the Microsoft Teams, but you go for the VLSI group. Okay.
Okay, all right.
All right. Okay,
All right,
guys, take care. Okay,
all right,
bye.